Welcome to the Techno-Optimist. This is number 5, right, Matt?
This is the 5th.
5th. Wow, this is going quick. I'm really excited. Today we have Randal Koene. He is a Dutch neuroscientist and neuroengineer. He's the co-founder of carboncopies.org, but also he is the science director of the 2045 initiative. Last week we went over all the mind uploading with the Tercerum network, and that was that was a good conversation. Was really, Bruce Duncan just really took us down a rabbit hole as far as what we could do with current technologies online. But today we're going to talk to this neuroengineer, neuroscientist.
We should also mention that we're on iTunes now. And
Absolutely.
You have that on the site at simulate.com. You can click right there, go straight to iTunes. And if you like what you hear, write a review, rate us, because all of that stuff gets added up, and then boom, there we are.
Absolutely.
In iTunes.
We would appreciate if you would do that. But let's go ahead and get Randal on the line and let him just take us through the mind uploading from his...
I'm excited for this one. This is going to be a great interview. Randal, how are you doing, sir?
Yes. Hi, very good, thanks.
Perfect. All right, Randal. Kevin here, and we were just going to jump right in. I gave you a short introduction, told them that you were the science director of the 2045 and the carboncopy.org, that you were the co-founder of that. Can you give us a slight overview, just real quick, of Carbon Copy? But then I really want to jump into the actual deep aspects of Substrate-Independent Minds.
Yeah, sure. So carboncopies.org is it's a big picture organization. The idea is that it acts like a science curation project, or like the foundations that have a specific goal in mind. So take, for instance, if there is a foundation that wants to cure Parkinson's, and then they do whatever it takes to get that done. The same idea is behind carboncopies.org. So it's an organization in which the main task is to keep track of roadmaps that show how can you get to substrate-independent minds. What does it take technologically? What are the different ways to go about it? What projects are out there working on cutting-edge science? And who are the researchers? And then get those researchers in contact with the right projects and find funding for them. So Beautiful. It's partly that, putting together the projects, and partly outreach to the public, making sure that people know what this is.
Sure, and that's part of your foundation is actually from the 2045 initiative. Is that correct?
Yeah, carboncopies.org was founded by myself and Suzanne Gildert back in 2010. I've been involved in this field since at least 1994.
Wow.
But recently, since May 2012, we've been supported by the 2045 initiative. And this means that what carboncopies.org is doing is now basically part of what 2045, if you look at their roadmap, what they used to call... Well, they have another project called Rebrain, which is very similar, and it's their Avatar C, how to create a new somewhere that you can transfer the brain to.
Sure.
I'm still not really used to the terminology, which trips me up a little bit, but yes, so we are now part of that effort. Yeah.
Oh, beautiful. Okay, can you jump into, now that we have that established, what you could define in the most layman way what substrate-independent minds are?
Well, what I like to tell people, first of all, is that it doesn't really mean that you would have a mind that does not require a substrate. When you think of substrate-independent minds, if you happen to be familiar with programming or something like that, it's very easy to see an analogy there, for example, with platform-independent code. Platform-independent code means a program that you can compile and run on many different types of computers. The same idea for the functions that make up the mind. What's going on between our ears here, the stuff that we require in order to live in this world and to experience it, you can also describe that as a number of functions, mental functions or mind functions. And substrate-independent mind is when you have been able to define or extract those functions in a way that you can then emulate them or run them in many different kinds of, let's say, hardware, where hardware means a kind of brain.
Okay, so let me try to break that.
I would draw the same analogy for me and you in mycology, where you have your substrate that you're inoculating with your spores.
Absolutely. I want to get into, though, the subjective sense of that. First, if this is going to be substrate-independent mind, we got to first establish some common ground of what we think of as a mind. And so how I understood your approach to this is that I, from my biology, from my genes, have coded for this type of program inside of my wetware, inside of my neurology. There's a type of program on there that you guys can then go in and copy that program, so to speak, or emulate that program that's arisen above my neurology.
Okay, I think it's a little bit difficult to try to just talk in computer analogies when we talk about the mind or the brain, because the brain itself is a piece of hardware that encodes its learning. Mm-hmm. So the software gets encoded into the hardware as you go on. So you grow new synapses, new connections between neurons as you're learning. Sure. This means that if you're going to extract the functions of the mind, you need to read out how can one neuron communicate with another neuron, and which other neurons does it communicate with? All of this, the entire architecture of it, all the possible connections, and the way in which the parts of that architecture operate, what functions they carry out, all of that you would have to emulate in order to really capture what that brain has been from birth and what it has become through learning, through exposure to the world,
sure,
what you are.
The overall connectome, right? And
connectome is making it too simple. There really are two main thrusts, and it's good that we're getting right into that, because there are two main things that are necessary in order to get at the functions of the mind, if you want to understand them, if you want to replicate them, whatever it is, which is the connectome, the architecture, the structure, and what we now call the activity map. So this is this new thing that Obama's administration has now also decided is important to do. It's kind of like between 2008 and 2012, the big new thing was connectomics, the connectome. Mm-hmm. And there's been some really good results there, because a lot of work has been put into the tools and into research. It became a hot topic. And then now, this year, finally, the hot topic has become the activity map of the brain. So a really high resolution mapping of what are all these neurons doing, what kinds of response functions do they have. Because when you want to define a system, if you really want to build a model of a system, this is where it gets into what I try to describe in some of my talks. You want to break it down into little pieces that are more easy to describe. And when you've done that by looking at the architecture and getting all the little pieces out, then you still need to figure out what are all these little pieces doing, and am I modeling them correctly? If you want to model that correctly, you need reference. You need reference activity that you can compare it with. And that's what the activity map is about. So that's really the second part of it.
Okay, so the activity map, would that equate to the qualia? I'm in the subjective sense, so I can understand. I want a foundation of what mind is, as far as what you guys are going to try to preserve with these mind uploading. I'm trying to get a good foundation from a neuroscientist of what mind can be defined. Is it the actual activity that happens through that map, the qualia of that that communication that is happening between the synapses?
Yeah, I think jumping to something like the word qualia can be more confusing than helpful, because then people are asking, well, what's qualia? How do I know what to describe that as?
Yeah.
I think it's better to just say, let's start with something really simple, because when you think of any device or any mechanism in the world, there's usually, it is exposed to something. There's some kind of environment it's in, there's an input it's receiving, and then it does something and it produces an output. The brain, just like any other organism in our body, like all of our cells, like everything we have, does the same thing. All the neurons are sitting there and they're receiving an input, they're producing an output. Our mind, it's something that's receiving a bunch of input from the environment as well as from our memories. So there's experiential input, there's input from what's happening around of us, and then it produces some output. It's doing something to it, it's processing it. It's an information processor. Mm-hmm. That's what it is. So we can describe in mechanistic terms what's going on. What is this information processing? That's what we call system identification. That's that process where you need to then map to in terms of functions. Now, qualia, it gets a little messy, because qualia sometimes the discussion gets into things that seem almost indescribable in mechanistic terms, and I'm not quite sure why that is, because to me, when people try to describe the process of how can someone, let's say, it's always this thing about seeing the color red. How do you see the color red differently than I see the color red? What's your experience of the color red, and what's my experience of the color red?
What salt tastes like, yeah, sure.
Yeah. then to me, as a neuroscientist anyway, it always seems not that mysterious because as you're being exposed to colors and to things that you're seeing, your brain is beginning to set up connections that make some kind of sense so that it can do something useful with that. Like, for example, stop at a traffic light. So you're setting up all kinds of useful connections. This is the synapses that are forming in your brain as you're learning. And the way that you're learning it, because you're being exposed to things in a way that's slightly different than someone else. No one else is having exactly the same experiences that you are. And also, of course, you're differing from everyone else slightly from birth because your brain was set up differently as it developed before receiving a lot of input. And so obviously these connections are going to be different, but it'll still be something useful. And there is a correspondence you can make because we do interact with the same external world. So there are signals that are the same, and the stuff that we eventually do with it, like stopping at a traffic light, is also similar. So there's a similarity on the input, and there's a similarity on the output, but in between, we may have set it up differently. There are a lot of different ways to build functions that work. And so it's not surprising that there would be some difference in the way those are built, and then also how things are experienced.
The difference
but to me, that's just the precise setup of that synaptic learning and the way in which those have become different because we experience different things.
Sure. And does that equate to our personality, our persona? Like what we individualize as ourselves is the differences in those connections that have set up through experience? Set up through different processing. So. And so does that where your techniques and technologies go through to map that personality, to capture that, so to speak?
Yes, actually. And so
can we jump into that?
A simple way to put it is that synaptic connections and the strength of those synapses, they represent everything from how you are going to control your external muscles. So let's say if you're a pianist and you have a specific way of playing the piano, some of that is encoded in synapses from your motor cortex. But then there are some that have something to do with your perception of emotions, but also that is being processed through a network of neurons and synapses. So again, it's that processing through these synaptic connections that's defining how that is then expressed. And this is your character. That's how you express, it's how you feel. But it all ends up being something about weights and synaptic strengths and types of neurotransmitters, all these biochemical machinery that's inside your brain. If you can indeed map that, or at least this is my thought, is if you can map that, then indeed you're capturing what is going on there. You're capturing your experience and your expression, which is basically you.
Yeah, you're individual. And so what are the techniques right now that we can get into that? The one that blew me away the most was those micro-sized blood cells, those microchips that were the size of a blood cell. And can we start with that and then go into the differences and all the different avenues that this is actually taking place to give people a good idea?
Yeah, I'm glad to go into that, although when I try to describe it, I always find it useful to make one little step back. We were talking about the brain activity map and about connectomics before. So what you're talking about now is tools that are directly getting into the brain activity map problem. How to get a lot of functional readings of activity in the brain at a high resolution all throughout the brain. And there are really three main paths in which research is being conducted and developments are happening to do that. One of them is by increasing the number of electrodes that you have in a typical array of microelectrodes to read from the brain, so a bunch of needles basically. The other one is to create nanoparticles that strengthen the signals that are coming from the neurons in a way that it becomes more apparent on the outside using imaging technology. And then there are the methods that are trying to get right into the system. And so that's where we're talking about either a molecular approach, this is the so-called molecular ticker tape, using synthetic biology to make something to record activity on.
Oh, can we jump into that? Not to derail you, but that one, the ticker tape, I understood that was that there's the same copy piece of DNA that becomes a ticker tape. You know, the changes of it when the neurons depolarize, it leaves an imprint on that DNA that we could read out. like ticker tape and see the differences or see the actual action potential happen within the DNA?
Yeah, it's pretty much like that. So you have a piece, I guess you could call it a short piece by definitions of what's short and long in DNA.
Sure.
A short piece of synthetic DNA and circular amplification happening inside the cell that this artificial DNA has been put into. The cell is a neuron in this case. So as the neuron has this amplifying circular amplification of the DNA going on, you're getting a long tape of DNA, which normally should be repetitions of the same synthetic DNA, but there's also a voltage-gated channel present, and every time when the activity in the neuron changes, it causes a difference in the amount of errors that are being made in the replication of that DNA. So then you can look at the errors on this DNA that you know what it's supposed to say, and that is your indicator of what the activity in the cell is.
Wow, so it's like, those little, they use them at sporting events, the clickers? So you put those little
like
tiny
that,
clicker thing inside of a cell, inside of the neuron, and it's just sitting there clicking, just counting the different times it polarizes?
Incremental.
Yeah.
Wow.
And you can see how this is useful because if you're doing that on DNA, it's small enough that it fits inside the cell.
Sure.
And you can use a vector like a virus or something else to deliver these to the cell and put them in all of the neurons at the same time. So then you're recording from all of them simultaneously, which is the ideal situation.
Where is that technology out at currently?
So this is being developed right now at Harvard and MIT as well as Northwestern. There are several groups involved in the development of this molecular ticker tape technology. And from what I heard most recently, they actually have ticker tapes ready for testing. Simple ticker tapes that are able to amplify and that are able to record, but where it is not yet established what their sample frequency is. So how fast can they record different signals? And I don't believe that that things like how to put them into the cell appropriately or how to get them out and read them out, that has all been solved. But the ticker tapes themselves, the first versions of them, they exist. And I think at the laboratories of George Church, which is where I last spoke about them with George Church, he said that they were now in the phase where they're testing those. So that's I find fantastic.
Absolutely. Can we? I mean, this is a perfect segue into go to the one that you articulate so beautifully. These micro-sized blood cell microchips. What do you?
Yeah, that's the other technology aimed directly at recording right at the sites of where activity is going on. It's basically, let's say you have, traditional microelectrode is like a long needle that you stick into the brain or into neural tissue, and then the tip is recording from some neurons, and the rest of the needle is being used to feed that data back out, for example. But that disrupts a lot of the tissue. What you really want is you just want that tip.
Sure.
That's what you want.
Yeah.
And that's what these tiny microneural interfaces, or what we call cyber cells at the moment, what they are meant for is to just do that wirelessly. And the ultimate target size for them is about the size of a red blood cell or smaller, which would be about 8 micron in diameter. There are a number of different groups that are working on this technology right now, and luckily it's not all competition. There's also cooperation, which is really necessary with a technology like this. Sure. The idea is borrowed from the way that the brain itself records what's going on or detects what's going on. The idea is, let's sit really close to the source of the activity. Let's use something small that doesn't disrupt any barriers, that doesn't break any tissue. And let's use a hierarchical approach where every individual cell, every individual recording device has a very specific, simple task. And together they perform this recording at many different sites, and then others have the task of transporting that information out until you get to larger implants that are able to communicate with the outside near the skull. So it's a hierarchical approach with many recording devices that are very small. And they're based on just using our silicon technology to put, let's say, up to 4,000, maybe 8,000 transistors on something the size of a red blood cell. That's enough to do a lot of interesting computation. As I often say, that's about the same as the number of transistors that were in the original guidance system for cruise missiles. So you can imagine that's...
So you have the processing power of a cruise missile, the size of a blood cell currently?
That is what is currently possible at that size. We don't currently have anything quite as complicated as that. Right now, the most advanced stage of this work, I believe, is at Berkeley, where they did some preliminary devices for implants, and they are somewhat larger than the 8-micron size that's the ultimate aim. And gosh, I don't know about transistor numbers, but it's on a prototype stage, I would say. The work that I'm doing, for instance, aside from carbon copies, I'm also involved in a startup that's called Neuralink, in which we're running through the feature tests for things like communication, power, localization, biocompatibility, all this on these types of recording devices to make a prototype.
I think I just wanted to establish that we currently do have the technology to put cruise missile technology inside of blood cells.
Oh, I see. Okay, yes, that in fact is the reason why I choose to talk about something at the micron scale rather than the nanoscale. Because we do have that technology. We have the technology to work at that scale. That's what we do every day when we're building any kind of CPU chip or something like that.
But cells are micron level, and cells are what we're trying to interact with and what we're trying to actually communicate with. Yeah. And so putting something the size of a cell and using the exact same technology, as I understand it, to go and sit next to a synapse and listen in like a microphone in on the communication that's happening, I would say that, I mean, that might, in my limited view here, might be a quicker path to get the whole brain emulation type of system online. I mean, the ticker tape, I think, is incredibly beautiful, but I'm not sure how you combined all that data and how you know exactly where the DNA ticker tape is from. But when you can have localized individual microprocessors that are sitting an array in marinating in the whole brain, and then being able to triangulate, and it just seems like when you have cells, you can track those a lot easier.
It's certainly very attractive from the point of view of having control over what's going on.
We know where to shoot a missile.
For me, it's very easy to think about in terms of electronics because it's something I'm more used to than synthetic biology. So for me, that's the target that's easy to go towards. I can see how you can program them. I can see how you can work with the data, how you can create networks in which you're processing what's coming out. You could use these devices as neural interfaces in addition to using them to record and then create emulations of what's going on in the brain. So there are a lot of very interesting uses for those kinds of interfaces. But this is something that I've learned over the many years that I've been working on the topic. It's not good to bet on a single horse in this race. So it's very good to have many different technologies that are aimed at solving the same problem. Because while it is easy to work with electronics and it's very versatile and we know how to do it and we know that technology very well, the problem of making it work well in tissue and making sure it has enough power and all this, there may be some roadblocks there that we haven't bumped into yet at this point. And at the same time, we know that the molecular approach it's an approach that is, it's automatically suited to the biology in the sense that it takes its energy from there. It works in that environment. Of course, there are other concerns then. If you're doing something, if you're tweaking the biology, then is it having any other side effects that you need to be aware of? So there are possible roadblocks and problems in both technologies and probably in all technologies that you could try to use to do this. Even, let's say, if you were just doing imaging from the outside, because anytime you try to ramp up the resolution from the outside, then you have to increase the power, and then it becomes potentially more dangerous to the tissue. Sure. So there are trade-offs, and it's great to have multiple paths.
And I think the multiple paths are incredibly important. I mean, I can see how this, a lot of that you preface with your talks is the dystopia versus utopia type of thing. And I'm sitting here currently as a bag of biology that is prone to a lot of different disease and disorder and bad engineering, also great engineering. But the fact that we have people like you that are setting out these roadmaps to actually fix that and take it to the next level shows that we already currently live in a state of vulnerability on this small skin of a rock, prone to asteroids and, viruses and all these different type of things, that I think it's paramount at this point that we do have all these different avenues, because it is something that we should be fixing.
Yeah, I mean, I'm not sure exactly how deep I should get into that part.
Oh, go please, as deep as you want.
They've said this a lot, but in principle, just to say it extremely simply, the reason we function well on this planet, or have done so for a while, is because we were evolved into this specific niche, this environment. Selection pulled out those things that survived well in that niche. But as soon as that niche changes, and if that niche changes at a rapid rate, or if we are transported to another kind of environment or another kind of challenge, then this isn't immediately true. We are not optimized or well selected for living in other kinds of environments. And by that, I don't just mean the biosphere or something, but the kinds of challenges, the sorts of problems that need to be solved.
Sure.
So you need to keep that in mind if you think in bigger picture, long-term view.
Yeah, I really loved what you were talking about when you talked about the astronauts that go out there, that they bring the biosphere with them. They bring their environment. They're not experiencing anything outside of what they evolved with. And they have to bring their all their senses inside of the spacesuit. I would actually really, really enjoy if you wanted to go deeper into the philosophical aspects of mind uploading, and if that's an area of speculation that you care to go down. Because I am like this techno-optimist that I do love to go very big picture, and I don't see the dystopian. I mean, I can, if I watch a lot of Fox News and stuff, I can see the dystopia, but I don't think with technology as it's helped us currently is on that scale. I like Steven Pinker's research, that the chances of dying at the hands of another man are lower than they've ever been, and so that adds to my optimism when I project a probable future. And so that's where I get into the speculative realms that I would love to pick your brain about and see where you see this going in 5 years, 10 years down the road.
Yeah. I personally, I'm happy to talk about those bigger philosophical issues as well. And by the way, I don't come at this at all from a negative dystopian point of view, although it's worth mentioning it. I find that there are really two big things that are worth mentioning. I come at this from the point of view that when I was younger, I wanted to do a whole ton of things. I loved art, I loved writing, I loved music, I loved all of this stuff, and exploration and learning. And it's just something where after a while I realized there isn't that much time and our capabilities are kind of limited. So it's not so much the negative of, oh, what's going to happen? Are we all going to end up in a dystopia in the next few years or so? But the original reason why this is interesting was for all the possibilities that would open up. So it's kind of not that we are forced out of our environment, but maybe we want to go into a different environment, or we want to attempt different challenges. And for that, that's really useful to go beyond what we currently are, to try to become more. So that's the one side of it. But it's also not wrong to point out that even though things are going well right now, even though technology and society has evolved in a way where, in fact, the chances of dying through violent conflict are less now than they used to be, and Pinker's right about that. This doesn't mean that there is never going to be a situation where our environment changes or where the challenges change. So just because it hasn't gotten worse doesn't mean that we don't have to continue developing.
Oh, absolutely. But I think that we're becoming a lot more empathetic as a culture, and I think that with the internet, and I really like Chalmers' the extended mind thesis, and I like to project that it's literally the extension of like our neocortical capabilities. That empathetic neural network is reflected in the social media sites that we see, and it's causing more empathy to actually come through our biology, I feel.
Yeah, I agree with you. I actually think that we have become a more empathetic species. If you just look throughout history and how we've changed the way that we behave towards one another and also towards the world around us, it's become increasingly empathetic. That's quite clear. And I think the fact that we communicate with one another more in different ways, at longer distances and throughout time, those are all very important. I think in an even bigger philosophical perspective, I like to compare how, okay, you've got entropy in the universe, that's the one thing, but on the other side, you've got this increasing complexity that you see on a planet like Earth, where at first you have no life, then you've got single-celled life, then you've got multicellular life, then eventually you get all the way up to humans, and now humans have created these means of building themselves out into a larger kind of organism that operates together. We've all become very specialized so that we're dependent on one another. We communicate a lot. We have not just our own brain in which to store memories, but also other ways of storing things from the past, so that stuff that happened in the past can now influence something in the future. Like when someone's looking at a picture, that's influencing them in a way based on something that was photographed in the past. Before pictures were taken, that didn't happen, so there wasn't that connection. The same way, if you have a connection between 2 points over a long distance, suddenly there's an interaction between points that didn't used to interact. So there's more complexity. The whole system's become much more complex and more interdependent. So it's like this increasing curve of complexity that you've got going on.
Sure.
And it's very interesting to see where that's going. It makes it very difficult even to do things like just to define what is self and where does it end or doesn't it end. Do we push it all the way out and say everything that influences me or that I influence is part of me? Or do we say I don't really exist because we're all really just part of the same big thing? Where do you put that line? As we become more connected, these things get really interesting.
Yeah, absolutely.
It's also one of the things that interests me the most about what I do is the fact that a lot of this very philosophical stuff becomes very practical, become things that you can experiment with and learn about. Things like self, for example.
So you were talking about entropy. I just wanted to kind of give you what I heard, and that this might be way off, but so life itself, I mean, from the greater perspective, galactic perspective, life can be seen as negative entropy, right? That okay. And so biological life evolved technological evolution. And so is technology alive with that type of perspective? And what then would be, the technology's digestion? And I would say it would be our attention, and its means of replication is through memes. If language is a technology, one of the earliest technologies of humans, then its memes cause us to make action and make creative associations, then that causes us to instantiate iPhones and, connections across time and space, through, this technologically mediated telepathy that Amber Case likes to talk about.
Yeah, I think I agree with you. And in fact, it kind of leads back to the bigger problem of definitions. What does it mean to say something is alive? What does it mean to say something is conscious? Depending on how you set those definitions, you always get a different answer. So if you say alive, it has to be something that has DNA and it's biological or something like that. Well, then technology is not alive. But if we redefine this in a way that's maybe more purposeful in our everyday discussions or in what we consider important to being alive, then maybe all of the technology around us is also alive in the sense that it makes up part of this complex interaction and ongoing activity that's happening.
Doesn't it become our exoskeleton? And doesn't that make us as biology the imaginal cells of the caterpillar that give rise, to the, electronic butterfly, so to speak? I mean, that in the higher perspective of what is happening, if you just observed Earth on a time-lapse type scale, you would see these primates start hitting rocks and picking up sticks and getting fruit and then sending rockets into space and then actually creating this extended mind with substrate-independent minds able to interact without the limits of space and time dictated by the laws of physics around them. Can you see that perspective? That's literally what we're evolving out into, is this type of electronic butterfly, and we're the imaginal cells that are metamorphosizing into it.
Yeah, I can see that perspective. It's the problem really that I'm having is that once you start to get very metaphysical, then you have to start asking many more metaphysical questions. So I totally see what you're saying, but then I'm starting to think about things like, so this whole rapid exponentially accelerating change and going out there and becoming more, going from sticks to rockets. So what does this actually mean in terms of what does time mean? Because if we think about it in a quantum mechanical sense, isn't time just an expression of the interaction of things? So if there's more interaction, then time gets compressed and all this other stuff. So I'm beginning to get into that very metaphysical mode here where...
Please keep going.
Yeah, it gets to the point where you have to question everything.
Absolutely.
And,
which I love. Terence McKenna talked about attractors, and I believe he called it the transcendental object at the end of space and time. But it's been called the omega point, and I believe Kurzweil calls it the singularity. But attractor, as far as there's, like gravity can be seen as an attractor that pulls, particles together. Well, at the end of time, say at the singularity or the time in which we compress all interactions into one singular point, you can see that we're headed into that trajectory. So there's an attractor that is actually pulling us towards that. And we're kind of riding on that exponential wave as we connect more and more.
Yeah. I can't actually imagine that omega point, I have to say, but I suppose nobody can. So while I appreciate all of these theories and I agree with a lot of the details as they go along, when it gets to putting a big label on it and saying something like singularity, omega point, and then kind of just going, wow, we're all going to be eventually compressed into one point and that's where everything happens, I find that a big leap. It's like, if you're going to make a huge claim like that, then you'd better explain what it is you're trying to say and how is it going to happen and get more into the details of it.
Engineer it, like what you're doing.
That's where sort of the practical, okay, how are we going to get it done part of me sort of shows up. Then I start thinking things like, okay, so you want to eventually get all the interactions into one point. What does that mean, actually? How can you carry out any kinds of processing or functions within one point? I can't currently imagine that. Maybe there's some kind of physics out there that I don't get yet where that's possible, but I just can't see it.
Sure.
Also, even if we say that eventually then everything is compressed and like sort of the entropy is then banished or whatever, that physically we know that that's not exactly how it works. We are conquering entropy locally by making more entropy elsewhere. We're, using a lot of energy from elsewhere in order to maintain the structure and complexity in our local environment. Well, how you could ever take all of the universe and structure it, I have no idea how that could be done. That seems like, unless there's, again, something in physics that we don't understand in that area, I just don't see how that's physically possible. So these grand claims, I love the trajectory that it's on. I love the understanding that there is more there than linear progress and all that kind of stuff. It's very important for people to understand that and look at the big picture. But then it gets to a point where I don't want to jump over into just pure blind belief in some kind of wondrous thing. I need to understand what it means and where it's going.
So let's use the technologies. Let's pull the speculative dial down a little bit and look at the technologies that are here. Say within the next 5-10 years that we actually have these little microprocessors or these little Tomahawk missile, cruise missile blood cells that are picking up all information in the brain. And once we have those in place, these nanobots that are getting the whole brain emulation, what happens at that point? What is it to actually have the subjective sense of substrate-independent mind?
Sorry, you asked what is the experience of it, or what was the final question?
What would it be like for somebody to experience? Like for me, myself, to upload and become substrate-independent.
Okay. That's a very good topic. Just before I run into that, I just wanted to mention that I don't actually consider these probes nanobots. That's
a very bad terminology.
It's not a huge deal. It's just that I like to point that out because nanotechnology and the notion of nanobots is something that's been around for a long time, and it's very complicated to really build nanobots unless, you're building DNA robots or something like that. So
microbots.
It's actually the reason why I think that these recording devices are more feasible is because they are not nanobots.
Sure. Okay.
That's sort of
Thank
they're
you
bigger
for the
than that. They're 1,000 times bigger.
I read about these in the 90s, from the Popular Science, and I've always been so excited about the computers in the blood cells, and Kurzweil has always been predicting that there's going to be little computers the size of blood cells, and it's always been on the horizon, and I've always been waiting, and now I'm talking to somebody
But I mean, they're here.
Yeah, what I mean. They're here.
If you take a regular CPU and you just cut cut out an 8 micron size bit of that, then you've got something with a ton of transistors on it. In other words, it's a little computer, and it's on the size of a red blood cell. So it's here. It's just that we haven't used it in that way yet.
Well, and that's what you're for, and your foundation is for, and we're going to plug in the carboncopies.org one more time. Yeah. But let's get into what it is to be a substrate-independent mind. Okay,
so before you are a substrate-independent mind, you have to become one. And the idea of a transfer to another kind of processing medium, an upload, first of all, there are a number of different ways that you could do that, and the experience could be different based on that process. So you could have the discontinuous approach, say you're creating a model of the brain by reading out everything that's going on in this activity mapping as well as the connectome, and then you build something that is the new processor for you, and then that could be you as well. So they've got this building something distinct and turning it on, basically, right? That's one possibility.
Sure. Yeah.
The other possibility is that it's all very organic, sort of one by one, replacing every plank of the ship of Theseus one by one. You're putting these artificial cells inside the brain, and instead of just recording, perhaps they're also taking over the function of a neuron, or each one transfers information to some other artificial neuron that's external to the brain that's taking over the function of one neuron or 2 neurons or 3 or 1,000, until finally you are operating on different hardware.
Well, currently...
that's just the transfer methods. But now imagine, aside from the question of which one is the better way to go, which is another philosophical issue, how should that process proceed? How much can you change about a person's environment at once before it becomes traumatic? I think trauma is a very important thing to consider here, because change is normal. We change all the time. I've changed a lot since I was 5 years old, and I'm changing right now, and so are you. But sometimes things happen to us where we change, and it's not good. And usually that's what we call a traumatic experience. Mm-hmm. So a very important aspect about any kind of change we undergo, either in society, having to go and get a pacemaker implanted, experiencing some kind of loss, or transferring into a new kind of substrate, any of these things need to be done in a certain way so that it's a positive rather than negative experience. And that's why, for instance, one of the things to consider is, how do you make sure that the amount of change that's happening is something that's acceptable to our experience of being?
But our assimilation with technology on a personal sense has been incredibly beneficial to the biological system. And I would say that the transition is happening. And I've made the case a number of times on this podcast that I resonate with the language that I feel as if I'm a technological being in a biological body, or my substrate is biology currently, but I can see that I assimilate with my iPhone as it's a part of my extended mind. It retains my memory. It retains a bit of my persona. My Google account, it is now starting to, infer what I'm thinking, and it queries against that and populates me with results. I mean, my assimilation into my technology is accelerating exponentially. It really is. I wake up and I'm on my phone. I live in the digital world, and so I think that adding little processors, that are actually going to complete this whole brain, it's going to be a smooth transition along that same curve. But I can see that technology on a cultural sense, because it's linear, technology can be used to harm biology, like bombs and all of those type of dystopic type of visions. But in the personal sense, technology has been incredibly and increasingly beneficial to our biology. And I don't think that there's a debate on the other side of that when it comes to science and comes to longevity of life and all the type of connections that we have through our technology. But on a cultural sense, of course, it can be, there is atomic bombs.
But isn't the idea that you're still interacting with this technology and you're still in a body? Like, you have your body you can always go back to. It once you're substrate independent, like, you lose that part. And I think that's a big part of the traumatic aspect of it, of how easy that that
There you
transition
go.
is.
That's,
Thanks,
that's
Matt.
kind of what I was getting at, because first of all, of course, when we talk about substrate-independent minds, nobody said that you don't get a body. People always ask, well, isn't it going to be weird to be in a computer or in a black box or something like that? And what do you do then? That was never actually said. We never said you shouldn't have a body. But it's a really good thing to get at that point, because that is really what I meant by the trauma. It's not what happens culturally. Is that traumatic? Sure, that's important too. But personally, if something happens, like say you suddenly lose your sight, that can be traumatic.
Yeah.
So if in a transition to a substrate-independent mind, a lot about your sensory input changes, or a lot about the way that you're processing time or something like that changes. Like let's say you're running faster or slower than everybody else. If there's a significant change that is kind of unusual to you, sure, you could get used to it, but how you're introduced to that kind of change matters, because that's whether or not it has a traumatic impact on yourself, on what's going on in your mind, whether you then start to incorporate new fears or anxieties or things like that.
Sure.
So there are reasons to be careful about that, which is actually a reason why I think Carbon Copies now working with 2045 is excellent, because the 2045 initiative looks at other aspects of the problem as well that I don't myself have time to look at most of the time, which is, for example, the body problem. What do you do about that?
Yeah.
How do you interact with your universe once you're in another kind of mind processor? Because there are so many options. You could live in a virtual universe. You could live in a robotic body. You could live in a new biological body. You could live in some kind of a hybrid. You could live in multiple different bodies in different places. Or there are so many possibilities. But looking at all of that just goes way beyond the scope of the problems that are central to substrate-independent minds, which is why I don't generally spend a lot of time on it. But I think working together with other people who do, as in the 2045 initiative,
Sure, yeah,
is perfect in that sense. It combines well.
Well, so if I understand this right, or what you're saying, and how crucial and important it is currently and today, that these conversations have an impact, and they're processed on a part of the brain through these conversations that don't imprint in a fearful type of dystopic type of, that trauma. You were using the word trauma. And so if they hear about these future technologies and all these advancements, and it's processed, say, through like the limbic or the amygdala type of processing, where it's fearful, that could be actually get to the point of like trauma PTSD, to where any time that they process new technologies and new technological innovations and discoveries.
Yeah, I think we're still talking about two different things, because I think you're still mostly talking about culture shock, future shock in culture, about people processing the idea of a new technology, whereas I'm literally talking about what's it like, because you wanted to know what's it going to be like to be in a substrate-independent mind, so I wanted to first address what's it going to be like moving from a biological brain
at the individual level,
independent mind, and how do you make sure that goes well? Because it could be as traumatic as having a piece of your brain being blown up by shrapnel or something, which would not be good.
Yeah,
you don't want that experience. So,
I guess I was making from the
Yeah.
case that we're currently. I would say most people on the planet are assimilating with the technology currently, and we're just going to continue along this exponential curve.
Yeah.
And with that curve, now that the assimilation has already taken place, it's happening. We're mid stages. We're upgrading. We're literally downloading.
So when you're saying that people are assimilating it step by step and in stages, which of course sounds like exactly the way in which you do not experience that kind of trauma, then you're automatically assuming a certain technological approach to uploading, because you're assuming that it's going to be a gradual process where you're assimilating new probes in your brain and you start to live with them, and eventually it kind of takes over your function. So you've already assumed a certain technological path, a solution to it, which means that yes, you've thought about the problem of trauma, at least implicitly. And that's why you've gone in that direction when you think about how it's going to happen. Of course, that's not actually something that's been established, right? It's not
sure.
that we know that that's the way that's going to be done, especially when you listen to very different views by researchers such as Ken Hayworth, for example, who really likes the notion of taking, say, a brain that is in fact already, I guess we could call it deceased, in the sense that it stopped functioning, and then you plastinate it, and then you cut it up and you create a model. And I mean, we're talking a lot in the sense that he's becoming quite open to the notion that the brain activity map is also important. So it's not just all connectomics, and that it's hard to infer everything from just the morphology. But the view is still like, okay, you can just take this and then create the model and then turn it on, where it's nothing like that process of putting cells in your brain and slowly getting used to the transition and all of that. You're suddenly in a new body, a new brain, and it had better be good, and it had better be pretty close to what you're used to, even though, compared to just not existing anymore, perhaps you're willing to accept quite a lot of trauma, a lot of change, but you'd prefer not to have a huge amount of trauma.
Yeah.
Because what if everyone is emotionally damaged as a result? You don't want that to happen.
Sure.
So it's important to consider.
I was absolutely making, based on the assumption of my own experience with technology and my life so far, and my subjective sense of assimilating with my technology around me, feeling as if it is an extension of my biology. And so that I was making those assumptions when I projected the future. And with projecting that future, I wanted to see where you felt the importance of conversations with the optimistic light and with the that future that doesn't entail the dystopia, because we have the research like the Pinkers and like you saying that we have a much more empathetic society. But the conversations that take place through the media and through a lot of politics and such are dystopic in comparison to the actual reality that we see. So I was trying to bridge where you see the importance of speaking optimistically and speaking with that type of passion and hope for the future with these technologies.
Mm-hmm. It's a bit of a media problem, really, because dystopian views, dystopic stories, it's kind of like war correspondence. These sort of things, they're interesting because they are very potent human, emotional, tragic situations you can imagine and get into, and it's actually our own empathy that draws us towards these sort of things and makes that big news item. So it's kind of interesting for news organizations to talk about technology in a dystopic way and what could possibly happen and imagine what that would be like. But you see at the same time that it's also very popular to talk about fantastic new medical procedures and things that weren't possible before, prostheses that are just amazing and stuff like that. So there are different ways to approach the problem of talking to the public about these futures, both of which can be interesting and both of which are going to happen. We're not going to be able to stop discussion in either direction. Of course, dystopic views are going to be presented and are going to be talked about. And it's a matter of talking about something so much that it becomes a normal part of the conversation and is no longer just some fringe, harebrained, out there kind of topic. Once things become normal enough, once you talk about them so much, then the sensationalism, it can still be there, but it's not going to be all that people know about it. They're going to know it as something that is familiar to them as a topic. It's something that is part of the social conversation.
Propaganda becomes opaque.
Yeah, the propaganda becomes just a small tidbit of the entire picture of what's talked about. And that's one of the reasons why I appreciate the effort that Dmitry Itskov is putting into the 2045 Congress and the ability to talk to people at many different levels about these possibilities and ideas. And he's not excluding the possibility that something dystopic will come up in the discussion, but just to bring the entire conversation out there and make it more normal to talk about.
Yeah, I think it's
and I didn't
beautiful.
used to do that myself a lot, because the truth is, as a researcher, when you're trying to work in this direction, when you're trying to work on these kinds of problems, you're walking a fine line where you need to make sure that you can try something new, something that's out there that's never been done before, and maybe even something big that requires a lot of forward-looking and putting together of big roadmaps and plans. But at the same time, you don't want it to come off like you're being naive, as if you don't understand what you're talking about. You don't want it to be just, something that someone who is trying to put together a research project within the constraints of funding proposal and whatever else can't really get around, can't see as part of their universe. Yeah. So for me, as a researcher, it's always been this fine line that needs to be walked in order to make all these things possible, instead of trying to do a groundswell sort of movement of, oh, let's do more in this direction, let's build a bigger future. That aspect is something that an organization like 2045 can do better than I can with a more research-oriented organization.
Absolutely. I mean, it takes both. It takes the people that have the time to dedicate to their articulation and their passion about these technologies, and then the people that actually take the time to create these technologies. I have a very, very, uneducated view on what your guys' work is, but by you guys doing that work, you're able to create the metaphors and create the type of language that allow me to understand what you're doing. And hopefully me taking the time to create these type of platforms, and like the 2045 taking the time to create those platforms, then we can get that media out to the masses, change that type of propaganda to actually show what scientists like you are actually, developing, like what you're saying that is actually here. I love that you say that the technology is currently here, that we can have cruise missile technology inside of our blood cells. That Kurzweilian type of dream that I read about in the 90s is actually here right now. It just has to be developed, and with that development, we need the conversations that go around it, so it becomes, like you're saying, a common everyday type of thing, and not something in the future. It is actually here.
Yeah, that I actually have tried to put quite a bit of effort into, which is to describe the whole brain emulation approach to substrate-independent minds in terms of projects that can be carried out right now and that are being carried out right now. So things that are feasible using the technology at the level that it's been developed right now, in the sense that the fundamental components of that technology exist, and we need to put together the devices and test the devices and go through that process of R&D rather than fundamental science. That's what I've been trying to point out, is it is the time to work on that. We're ready for this, which is different than for example, assuming that at some time in the future we're going to develop nanobots that'll take care of X, Y, and Z, or that we're going to have, I don't know, some kind of superluminal drive that will get us to the stars.
Quantum computing and that. That's...
So it's not that all those things are impossible. I mean, a lot of them are probably going to happen. It's just that in many of those areas, the fundamental science or the fundamental processes and things that you need to be able to do with our technology are not quite there yet, so that hard work is necessary, but you also need to bide your time and not make huge claims about exactly how something's going to be put together yet. But in the case of whole brain emulation, it's actually interesting to see that that's not true. The technology that we have today is up to the task of building the devices that we need to get the data, to be able to carry out the processing. It's not beyond our current state of technology, so we don't even have to wait for the Kurzweilian curve to catch up. That curve will help a lot in terms of making things even better, faster, cheaper, etc. But we can build these things now. We can do the projects. We can do the work. We could create the tools necessary to extract the data from, say, the brain of a Drosophila, the fruit fly, and build an emulation of that probably within the next 10, 15 years. That's within the scope of a project that you can fund and plan for right now.
Wow. Well, I think that's just so... it is here now. I mean, I was just thinking when you were talking about all these future prospects like the quantum computing and the warp drive that NASA's going into. These are all speculative, great. I love that they're pushing innovation to those. But again, you're saying that the current technologies that we see on the Kurzweilian curves in the future, you're saying that we're behind the curve. As in,
well, we're not behind the curve.
Not behind the curve, as in the curve is here. We're there. We have the current tools to implement what is on that curve to make it.
Yeah, it's a very simple statement, really. I used way too many words. I should have just said whole brain emulation and the technology that is needed for it is a feasible project at this moment. It's not one of those speculative projects where you don't know if the technology is possible, if you can even do it. It's technologically feasible.
Wow. Well, I think that's absolutely something that we should be doing. I'm glad that you have the foundation, and I'm glad that we can have a platform in which to get your message out there. Carboncopy.org. We are up on the hour mark, and it's depressing me to no end to think that this went that quickly. Is there any other place that they can reach you? Reach out to not just the 2045, but the Carbon Copies. I know you have
There are two main areas where I connect with the public or with anyone who wants to get information. One of them, as you said, is carboncopies.org. So that's carboncopies with an S.org. There you'll find lots of information and contact info as well, so that's quite easy. The place where all the news updates happen and there's quite a bit of discussion is the Carbon Copies group on Facebook. And I know that a lot of people don't use Facebook, but it just happens that it was very easy and it facilitated discussion. So while there are also other forums and mailing lists, that's our main
I enjoy that group. I've been a part of it for a couple weeks now, and just fascinating discussion happening. Really good contributors on there, and I really enjoy it actually. And yeah, Facebook isn't the normal for these type of discussions, but it definitely, I think it is a good platform in which you can have deeper discussions. I like all the links there. Matt, anything?
No, thank you very much. That was a really good discussion, definitely.
Randal, this was an opportunity. It was a pleasure. I do, hope that we can do it again in the future. And we will talk to you again. All right.
Yeah, thank you very much. I really enjoyed myself, and I hope you guys come to the Congress.
Absolutely. I hope that we can see you there. Actually.
Okay. Thank you.
All right. I appreciate it. Thanks, Randal. Matt,
dude.
These guys, I don't know if I can keep up. Each week it's just getting, we had Maria, the life extension, everything about, extending your life beyond what biology was programmed for. And then we got into where I was able to use a satellite to upload my persona, my digital data up into the stars. And now we have this neuroscientists that are working to pave the way to substrate-independent minds, saying that, there's technology to put, cruise missile technology inside of our blood cells currently. This stuff is just incredible. I'm really fascinated by it all.
Yeah, that was great. He was very, just everything that he talked about, he was really into. This is really good work, definitely.
Yeah,
and you have to build upon that. Everybody's bringing this technology together to build and build and build, and you can't just get to the warp drive without building all of these parts in between.
Yeah, I love that he just kept bringing it back to that we have to do the work. You know, he does have that side. I kept trying to bring him into my huge optimistic bubble where I see this utopia that everybody's hugging, and he goes there just a little bit, and then he goes right. He's very realistic, but he's also optimistic, and I really enjoyed the talk, and it really was an opportunity and a pleasure.
That was good stuff. Who do we have for next week? Do we have anybody lined up for next week yet?
I think my brother, man.
Is your brother going to come on?
He's coming up, and that should be really fascinating. He has helped in my evolution quite a bit, and
that's cool.
Him himself. He has come quite a long ways, and he has a great story to share. And so I just really enjoy talking to him, and I think that the viewers would appreciate that as well.
Nice.
And next week. As well, Simulate.com, it's blowing up. It's really exciting to see. We have a bunch of people that are wanting to be contributors, and I love it, but it has to go through the editor, Nicole, and she's really great about it, and she loves the submissions, and you can go online and on Simulate.com and write to her your type of submissions. We have one coming up it was a research paper done for her college course, and it was all about how techno-optimism has really changed her perspective on life, and so that's going to be really cool to feature up there. But other than that, man, I think look forward to doing it again next week.
Yeah, definitely. We're on iTunes now, so make sure you guys check that out. And next week.
All right, we'll talk to you guys later. Thanks.